Hello everyone and welcome to Understand Chemistry. I am Dr. Bilal and today we are diving into the topic of free radical polymerization. In this video series, I will cover some key aspects of radical polymerization including monomer and initiator, the role of inhibitors and retarders, the mechanism behind radical polymerization, the kinetics that determine the rate of reaction, and the thermodynamic that influence how and why the reaction proceeds. But this video is all about monomers suitable for radical polymerization. So let's get started. At first, let us take a brief look at the overall classification of polymerization. Polymerization processes are broadly divided into two types: step growth polymerization and chain growth polymerization. Step growth includes mechanisms like polyaddition and polycondensation, while chain growth polymerization can occur through coordination, ionic, or radical pathways. I have already uploaded my lecture on difference in chain growth and step growth polymerization. Also, you can find a detailed video on step growth polymerization. Free radical polymerization is a type of chain growth polymerization in which reactive species are radicals. These radicals initiate and propagate the polymerization. The general mechanism of free radical polymerization consists of three steps: initiation, propagation, and termination. The initiation step consists of two steps: initiator decomposition, where an initiator is decomposed to produce radicals. In the next initiation step, these radicals attack the monomers to initiate the polymerization. In the propagation step, the radical add more and more monomers after another. This repetitive process builds long polymer chain represented in this equation as RMN radical. Termination is the ending of the reaction. During the termination step, the reaction has to stop. That can happen in few ways.
The first way of termination is combination. In the combination, two growing chains are combined together to produce one dead polymer chain. The second way is disproportionation. In disproportionation, one chain transfers a hydrogen atom to the other, which stops both chains from reacting further. This process produces two dead chains. The third way of termination is chain transfer. During the chain transfer, the growing polymer chain is dead by transferring its radical to another molecule, or we can say transfer agent, which is represented in this equation by Ta.
Now, the question is what type of monomers are suitable for radical polymerization. In principle, all the monomers that can stabilize the radicals are suitable for radical polymerization. There are simple basic concepts to understand. With the help of these, one can easily recognize just by looking at the structure of monomer whether it can be polymerized by radical polymerization or not. Here are requirements for the monomer to fulfill in order to qualify for a radical polymerization. The monomer for radical polymerization must contain carbon-carbon double bond or carbon-carbon triple bond. Usually, vinyl monomers are prone to radical polymerization. These vinyl monomers are of two types: monosubstituted monomers, that is of the type CH2CHX. The CH2 of the vinyl group is sterically unhindered and highly accessible for the radical attack. The second type of vinyl type monomers are 1,1-disubstituted monomers. These monomers are suitable if one substituent is small like hydrogen or a methyl. We will see later in detail how these monomers stabilizes the radical. At the end of the discussion, I will also show you examples of some monomers that cannot be polymerized by radical polymerization and why. The nature of the substituent X is crucial to understand whether a monomer is suitable for radical polymerization. Often, the molecules having mildly electron withdrawing substituents X, for example, chloride, cyano group, or a nitrile group, esters, acetates like OCOR, or phenyl zinc are favored for radical polymerization. These groups stabilizes the propagating radical through resonance effect, inductive effect, and hyperconjugation, also called no-bound resonance. Now the question is why radical stabilization matters. This stabilization is critical for controlled chain growth in radical polymerization reactions. Actually, the radical stabilization raises the activation energy required for termination reaction much more than it raises the activation energy for propagation. High activation energy for termination make it slower relative to propagation, reducing chance of early termination. The second consequence of presence of this type of constituents is that these also allow for controlled chain growth. This results high quality polymer or polymer with longer chain length. Now I will show you some most common monomer that can be polymerized by radical polymerization and the dominating factor that stabilizes the propagating radical. Let's start with styrene. In styrene, the benzyl type radical is strongly stabilized by the resonance into the phenyl pi system. In acrylonitrile, the nitrile group exerts a strong electron withdrawing inductive effect and delocalizes the unpaired electron via resonance into the C triple bond N pi system. This stabilization of the propagating radical raises the propagation rate and suppresses premature termination. In acrylates, for example, in methacrylate, the ester group COOCH3 exerts a strong electron withdrawing inductive effect, polarizing the carbon-carbon double bond, making it more susceptible to radical attack. Resonance delocalization of the propagating radical into the carbonyl pi system stabilizes the radical and accelerates propagation. In methyl methacrylate, the alpha methyl group provides hyperconjugative stabilization, while the ester moiety exerts a strong electron withdrawing inductive effect and donates via resonance into the carbonyl. Combined, these effects yield a relatively stable propagating radical and predictable molar mass. In the acrylic acid, carboxyl group withdraws electron density via strong electron withdrawing inductive effect, while resonance delocalizes the unpaired electron into the carbonyl pi system. In case of vinyl acetate, the acetate ester withdraws electron density through electron withdrawing inductive effect, reducing radical reactivity relative to simple olefin. In acrylamide, the amide moiety exerts a strong electron withdrawing effect, polarizing the carbon-carbon double bond, making it feasible for radical to attack. Lone pair resonance donation from nitrogen into the carbonyl bond stabilizes the propagating radical by lowering the radical energy. Ethylene has no substituents. The ethylene radical lacks resonance or inductive stabilization. Its high intrinsic reactivity drives very fast propagation but also leads to significant chain transfer and branching. In 1,3-butadiene, resonance across the conjugated dienes allow the unpaired electron to delocalize. The resonance stabilization reduce propagation speed and favor controlled growth. In case of 2-methyl-1,3-butadiene or isoprene, conjugation across the 1,3-diene system delocalizes the radical over two double bonds, providing resonance stabilization. An adjacent methyl group further stabilizes the radical through hyperconjugation. The next monomer in my list are the halogen-containing monomers. The first one is the vinyl chloride. The chlorine substituents withdraw electrons by negative inductive effect or electron withdrawing inductive effect, stabilizing the radical slightly, while its weak resonance effect is negligible. This balance yields moderate radical stability and mild mid-range propagation rate. The second halogenated monomer is 1,1,2,2-tetrafluoroethylene. The four fluorine substituents create an exceptionally strong electron withdrawing inductive effect. The resulting electron deficient radical exhibit very low Kp value, rate of propagation value, very low propagation rate constant value, that requires extreme pressure and temperature for effective polymerization. Now let us talk about the monomers that are not qualified for radical polymerization. For example, propylene. Methyl group in propylene is weakly electron donating inductively, that destabilizing the propagating radical. Highly prone to chain transfer instead of propagation, this can be polymerized by coordination polymerization. In case of isobutylene, 2-methyl group strongly destabilize the radical inductively and create static hindrance that forms very unstable tertiary radical. Isobutylene is preferably polymerized by cationic polymerization. Vinyl alkyl ethers has a strong electron donating alloxy group that destabilizes the radical inductively, but this is highly reactive towards cationic polymerization. The 1,2-disubstituted ethylene, like 1,2-dichloroethylene, have severe static hindrance, hence it prevents efficient radical addition or propagation. So this cannot be polymerized by radical polymerization. In fact, this polymer cannot be polymerized by any of the polymerization technique. However, CH double bond CH2Cl2 1,1-dichloroethene can be polymerized by radical polymerization. Hope you understand the concept, what type of monomers could be used for radical polymerization. If you want to study further, please consult these books. These are very nice books on this topic. Thanks for watching.